So moving along and continuing the things in data preprocessing, because like we say, data preprocessing, EDA, etc., is the major chunk of it. So transformation, all right. Now that's again a very gray area amongst data scientists, and definitely a cause for arguments and the temperatures run high. This is better, that is better, etc. So I would want Barney this time to speak first about what do you feel is a good transformation technique vis-a-vis the project that you have done, and the reasons why you chose that particular transformation technique.
Sure, absolutely. So, basically, there are multiple, times when you want to transform your data. One such reason would be if your data follows a non-linear pattern. What do I mean by that? If you plot the data and if you look at the distribution of the data, if the data falls along a straight line, you say that that's a linear pattern. However, when we have plotted income in the loan default prediction model, we were seeing a curve which was expanding or which was growing rapidly until certain time it was increasing in a linear fashion, and then we have seen a sudden increase. And you ask any economist and they would say that income as a variable will follow the upward curve kind of a format, kind of a pattern, which is called as exponential pattern. When you have exponential pattern, then if you use that income variable as is in your prediction model, it will not give you good results. It will not be able to capture the patterns well. So what are you expected to do then? We are expected to perform a transformation which captures that pattern in a nice manner. And one such transformation which people employ when your variable follows exponential distribution is log transformation. The moment you apply log transformation, the exponential patterns in the variable would be captured properly. So the point that I'm trying to drive is you have to do your exploratory data analysis properly. You need to look at your probability distributions and understand whether the variables are following linear pattern or exponential pattern or some kind of polynomial pattern, etc. And based on that, you will have to include the appropriate variables in your model so as to get good accuracy. So instead of using income in your model, you need to use log of income. Why log of income? Because that's following exponential distribution. And in this case, we were lucky that we came to know that it was exponential distribution. In most cases, the distributions would be very dicey. By just looking at the variable, you might not be able to figure out what kind of distribution it follows. And that is when we need to experiment. We can do a log transformation or exponential transformation or square root transformation or cube root, so on and so forth. And the question which often we encounter is, how many such experiments do I perform? For how long do I perform? It is directly proportional to the amount of time that you have on your project. Certain clients might say, we want to complete this project in 1 week. So you might not have the luxury to experiment a lot of transformations. Certain customers might say, I'll give you 3 months time. Okay, if 3 months time is provided, then you need to keep experimenting, more experiments, right? The more you experiment, better would be the results at the end of the day. That is one scenario. Another scenario is when your data are non-normal. When your data are non-normal, you cannot apply certain statistical techniques, because when people have come up with those algorithms and techniques, they build those algorithms assuming that the underlying data are normally distributed. So the moment you know that data are non-normal, you cannot apply these kind of techniques. If you cannot apply the techniques, you cannot glean meaningful information from your data. So it warrants an additional step of doing transformation. And through transformation, if your variable becomes normal, wonderful. You can apply all those techniques which assume that your data should be normally distributed. Right? And in a few other scenarios, we use transformation, but predominantly on our project, these are the scenarios where we have used that. Yeah, thank you.
Thank you, Barney. Thank you for that detailed answer. I'm sure that was quite helpful for the audiences here. So, Sharat, anything you'd like to add? Anything with your experience you'd like to add further?
Yes, just to add to Mr. Barney's answer, um, I would probably take a route of the statistical way to explain things here. The thumb rules in statistics that we use, the logic that we are using for EDA and trying to extract information, um, there is some standard thumb rule, right? So the representation of the standard thumb rule is done using a standard variable. It's a pseudo or theoretical variable, theoretical data, which is represented by Z in statistical terminologies. We call it as standard normal random variable. Now, the world as is to be assumed that it is a normal place. So that means the data that we are going to consume and start working on is also assumed to be normal. When I say normal, that means we don't have exceptional cases in the data. Now, if I have exceptions, then the analysis takes a different route. If my data is normal, then I can directly apply a lot of statistical calculations, theorems, which are already defined, like Mr. Barney was saying. So it becomes easy for me to analyze the data. So if my data was not normal, in our case, in my case, the fuel efficiency, which is the target variable itself, was not normal because we had exceptions. Like we had a couple of cars which were giving us very, very high efficiency, like 31.5, something on those lines. Exact number I couldn't recollect, but it is definitely very high. So these were abnormal. So when I wanted to work on this particular data, I had to ensure that it is converted into something called as normal distribution. So what we do basically is we compare the distribution within the data with this standard variable. One of the key characteristics with the standard variable is that it is identically distributed. That means the difference between the points, data points, is evenly spread. If your data also has this kind of a spread, then you can safely assume that it is normally distributed. So this was a comparison that we do. This is what we do. And if we identify that this comparison is not similar, then obviously, like Mr. Barney said, the distribution will show, the image will show a non-linear shape in the two-dimensional diagram. We generally call it as normal QQ plot, as we all know. And in order to transform the distribution of the data, rather than applying manual techniques, because there is no end to experimentation here, and we don't have any standards to say that if data seems to be in this form, then it can be declared as, or it has to be declared as normal. It's more of a subjective decision that we take. So to ensure that we have some kind of a consistency, we try to use the standard libraries, which are basically doing all these experimentations in the backend using some mathematical formulas, and gives us the best transformed data. So this is one of the library that I experimented with, was Box-Cox transformation. And it automatically takes care of all those iterations in the backend to check what magnitude conversion to the original data will ensure that it becomes normal. So this is basically how transformations is becoming very essential, and how we treat this as this non-normal data also becomes very essential for our project work.
Thank you, Sharat. So quickly stepping out of character, I'm supposed to be the interviewer here. So in my experience of training people and telling them about how EDA and data pre-processing will take up enormous amount of your time towards all these activities. And I also used to tell them that you will actually feel like plucking your hair. But during the training, everybody focuses on the algorithms, which is also good, but kind of at the cost of these EDA and data pre-processing techniques. So I've had many participants come back to me and said, "Sir, you are right. Absolutely correct. It's been 20 days and I'm still, working on the data, still doing this. And so much of pressure is only, I've not even decided whether I want to go for what kind of algorithm, let alone start working. I'm still on the data, understanding the data phase itself." So that is the reason why the three of us with our experience are trying to push you people to impress upon your interviewers who are going to interview you, to tell them that this is the problem. Because if you try to focus, this algorithm I used, this many techniques I did, this, it's more, it kind of tells you that you are kind of bookish. You really don't have the hardcore experience with reference to projects. Because if you've had, if somebody will ask you what were the problems you faced, this algorithm did not work, so we tried a different algorithm, straight away the interview will know this is something not, I don't want to use the word fake, but yeah, this is something fake. All right. So that is the reason why we are focusing here. All right. So I think we've run out of time, but I'll just, give Barney one small question to quickly wrap up today's session. The question is with reference to scaling, Barney, Mr. Barney. Could you explain to me, rather than what scaling you have done in your project, for want of time, I'll restrict it to why scaling is necessary, generically speaking.
Okay. So if you take an example of the kind of projects which Sharat was handling with respect to automotive, if you have an output variable called mileage, right? If you want to predict mileage of a vehicle, and say you're measuring the weight of a vehicle in kgs, you'll have some number, say 100 kgs. If you put that in the prediction equation, this specific value, then you'll get some mileage. However, if I were to change the units of weight and change that to, for example, pounds, so 100 kgs will become 220 pounds. In the same equation, if I use 220 and then do the calculation, the mileage will skyrocket. For the same vehicle, just because I'm measuring the weight in pounds, the mileage should not be high. Just because I'm measuring in kgs, mileage should not be less, right? So mileage should not vary based on the units that I'm using. If the units are in kgs, it'll be a smaller number. If the units are in pounds, it will be a bigger number. Your model should not be impacted by that, right? So that's one reason why we use scaling. Another reason is whenever you have algorithms which use distance, for example, clustering algorithms or your KNN algorithm, your SVM for that case, which also calculates the distance. Whenever you're using algorithms which calculates the distance, if you want to calculate the distance between two records, and say you have one column called age will be usually in 2 digits. And say you have another column called income, that will be in 4 or 5 digits, depending on the currency that you're using, right? So here, the column called age will have least influence on the distance because it will be of smaller scale, 2 units, 2 digits. Whereas when you look at income, since it'll be of 4 or 5 digits, that will have very huge influence on the distance. Your model should not work in that way. All of your variables should have equal influence on distance. So that is also another reason why we need to scale the data. So one golden rule is that the moment you look at the data, if you have different columns of different scales, meaning one column has 32, 33, 34 in that way numbers. Another column has 100,000, 200,000, 300,000 in that way, bigger numbers. Then you just need to perform scaling.